cool. The modes of operation on the equipment available are manual heating. So you could set the power and start, stop timer based. You could set it on preheating, where you could say, I want to preheat to a particular temperature. Then you would have to give a temperature feedback to the equipment. A thermocouple or a stitch type thermocouple or a touch type thermocouple or an optical thermocouple, anything is possible. You need to have a temperature feedback onto the system. And then you could heat to that temperature and hold it there all throughout your welding cycle. You could monitor your interpass temperatures. It could give you an alarm saying maybe you are, going beyond your interpass, stop welding. It allows you to do the complete PWHT cycle that we discussed. It allows you to program your hydrogen bakeout cycle. And it also allows you flexibility to customize your own cycle. We did do a very critical job right now for DRC along with Godrej, where we were to control the temperature very closely under 40 degrees at a 70 thick vessel. On the bottom of the vessel was where we had to do the normalizing of the temperature, and the entire program went on. It was a special customized program we did to ensure minimum difference, and it was on for more than 36 hours. And this cycle has been proven, repeated once programmed, it's repeatable, it's proven down to that level. We'll share some of the applications which are very easy and repeated and are on the shop floor seen by most of us. Please post all questions on the Q&A. We will take them in some time as we go along. So few of the applications that we'll be discussing today, pipe headers, T-joints, preheating, post-heating, backhoe buckets. So you could see the buckets, preheating of the buckets, stone crushers, long seam of pipes, and shrink fitting of bearing bodies. We'll also see a couple of other components. P91 pipes, headers, and T-joints, they all need to be preheated, post-heated, PWHT, hydrogen bakeout, everything has to be carried out. This is the kind of setup. You could see an equipment here, the coil being wound on the edge of the header, and then once switched on, it will go through the, right now the heating is on, it would have taken the temperature to the level desired. Typical setup for preheating, if you look at it, you could have set up the job like this. This is a huge elbow and flange. Here you have to preheat up to 250 degrees. Thicknesses are about 70 mm or so. If you were to do this with gas or with an electrical pad, the amount of time required to wind this on an electrical pad itself would be close to 2.5 hours, because you can imagine the kind of curves that are there. Whereas this in induction would take you about 10 to 15 minutes to set up. Just put the serrabull, wind the coil like you wind a row, fit it, and you could start. The root runs or TIG welding being done, subsequent runs of SAW or arc welding being done, the coil is in place and not a problem. You could keep welding while the coil is there and maintaining or monitoring your interpass temperatures. I'm sorry. Here, similarly, you could see a bigger vessel, a long seam of the vessel needs to be done. You could have a prefixed blanket like this placed there. Imagine the ease, the blanket never gets hot, right? You place the blanket here, leave it there for 20 minutes. This is a 50 thick vessel, if I'm not wrong, 3 meter or 2.5 meter long. This would have heated up in about 20 to 25 minutes, up to 200 degrees. Remove the blanket, start your welding, not a problem. Here is a comparison with gas-based system. This were trials done for one of our customers. If you look at this pipe here, it needs to be cladded from inside. So the temperature needs to be ensured that it's on the inside, the temperature is correct. And the temperature to be achieved was about 240 degrees. The wall thickness is about 25 mm. As you can see, the ID is 117, OD is 167, 50 thick. So wall thickness is about 25 mm. This is the burner that was used. And the burner, while the job is rotating and the burner is at a fixed position, when they tried to heat the zone of 400 millimeters, they were able to achieve 240 degrees in 20 minutes. But again, if you can see burner hitting at one time, you will have bright hot spots on some places and not so hot or equivalent temperature of 240 degrees all across the surface. However, in induction, we inserted the coil on the inside. And while the coil, this is the inductive coil, the job is still rotating. And while the coil is placed inside the heating zone of 400 mm, you are able to achieve the same job in 8 minutes. Now, while this is happening here, the operator cannot approach nearby because you can see the heat around. Here, the operator has no difficulties monitoring the temperature from the top or inside, and the ease of setup, putting the coil in and out, is as simple as putting a rod in and bringing it out. No difficulty, as this doesn't get heated itself, right? 8 minutes to 20 minutes. This is the kind of setup or running time saving, right? Again, if you look at the OD, here is a very heavy, thick component being preheated. So again, with gas, it took about 16 minutes to bring in the temperatures on the surface. No way to measure it on the inside. However, here, since the heating is happening from inside, when you measure on the surface, it's ensured that the heating inside is equivalent or above the temperature. Again, assured much lesser time, much better accuracy of heating. This is another trial done for its equipment in use for pipe to elbow welding. During welding for this material of P91, the temperature, preheated temperature was at about 150 degrees. It was achieved after 15 minutes. You can see that. And the job thickness is 72 millimeters. Achieved in 15 minutes, 150 degrees. They could start welding. All thermocouples all around, all across the 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock positions gave more or less consistent reading between 1 to 2 degrees. They started the welding. And during welding, as the temperature rises, and they stopped the welding when they could. The time required to preheat was very less, as you can see, hardly 15 minutes. Setup time on something like this, again, would be not more than 15 minutes. As you can see, you have to just put the serrawool on the job. These are the white induction coil. You could wound it, take a loop around, wind on the other side, take it back to the equipment, connect it, press start. As simple as that. Similar job here being done for post heat. We had to achieve temperature of 750 degrees. As you can see, it's achieved the 750 degrees after ramp. It is undergoing soaking for about 100 minutes, and then it will come down to 300 degrees in again a controlled slope of 40 degrees or 50 degrees per hour. This is the way the job is wound. This is a blanket, the serrawool blanket, and along top of which they have wound the induction coil. This you can see the profile of heat generated on the inside. Now imagine you are doing a post-weld heat treatment job on a power plant piping station, right? The job itself is couple of 50, 60 meters above the ground. So you are standing somewhere at this height. Now you have a joint like this, which is in between two pipes already placed. How are you going to place your, now try, imagine putting anything here other than induction. Try it with a, say, blanket, for example. The amount of time required and effort required for the operator to fit in the blanket or the electrical pads there and then wind it over would be much higher. A lot of time, lot of difficulty to do that. Here, it becomes much easier. Put the serrawool on top of the job first, then wind the coil and bring the coil to the junction box. And the junction box and the equipment could be as far as 30 meters away. The equipment is 30 meters away from the joint. The cable, the coil itself is 30 meters, and you have a 15 to 30 meter interconnection cable. So this kind of flexibility is available. Another very critical application for aerospace right now happening. This material here is non-magnetic and also has a very typical challenge where it needs to jump from 650 to 850 under 2 minutes. Otherwise, the heat treatment won't be correct, or it will not reach its desired solution. The way to do this was in two shifts, two parts. So we built a portable oven around the job itself. We wound the water cooled coil and preheat it up to 650 degrees and hold it there for an hour. Entire job is at 650. This job is then immersed into a existing furnace, which is already fired up at about 1100 degrees. That's the only way to achieve this solution. Otherwise, it's not possible. And this was really, really a tricky part to achieve the desired results here. As you can see, even the shape, right? Imagine this shape. It's a very difficult shape to preheat. You can see more thickness here, less here. By putting it into an inductive zone, we are able to balance and maintain the heat inside Once at 650 degrees, it stabilizes for an hour. All parts are equally heated. Cross-country pipeline, another popular application where you can see a lot of induction used now. An induction blanket can be to the size of the pipe itself. So you could have an 18-inch, 24-inch, 32-inch, 40-inch blanket. The time taken for a person to wind the blanket on top of the job, less than 2 minutes. Preheating time to reach 150 degrees, again, less than 2 minutes. And you can see the equivalent profile all across. The other way around from this is using gas to preheat the surfaces, not usually able to get equal heat, and also the risk of overheating and ruining your coating on the other side. This has been successfully executed on many GAIL projects across India. More than 50 equipments of this nature are working in India and now also in the Middle East. Pretty much a standard application for pipeline preheating. Again, if you look at the Higgs bucket, it's got about a 20 mm thick to a 40 mm thick plate needs to be welded here. The tooth that goes on each side is about 60 mm thick. Materials are Weldox and Hardox here. And the challenge is to preheat them above 205 degrees. The way to do it with induction, we place the coil here, a simple blanket, cerable blanket below it, and you could achieve 205 minutes in under 5 minutes. Again, the operator could simply pick the coil, put it on the side, and start welding. Okay, this if you had to do with the help of a gas-based furnace, you can imagine this would take at least 20 to 25 minutes to preheat. To remove the gas burner from there and get the welder to start welding would be another challenge. When they are welding the corner teeth, they need to preheat both of them at the same time to avoid distortion, and welding also happens parallelly. To do that, the same equipment, the one coil has been made, split it, the second coil has been wound here and goes back to the equipment. Both the joints have same thickness, same geometry, 40 plus 60 mm. We were able to achieve the time of 310 degrees temperature in about 10 to 12 minutes. Setup time under 5 minutes, 10 minutes to begin with. Again, 20 minutes, your job is out. Time taken to require to put the coil in place, to remove and start welding, under 5 minutes. You see, if you were to do gas-based heating, 10 minutes would be setup time. In induction, 2 to 5 minutes setup time. Heating time, 20 to 30 minutes in a gas-based system, whereas 4 to 5 minutes on the induction heater. Safety, the gas flame is always on, so somebody there has to be careful. The surrounding area is getting hot. Here, no flammable gases to be handled onto the shop floor, extremely safe as we shared earlier. Cost saving, gas used over 30 minutes versus electricity used over 4 minutes. Electricity used over 4 minutes, even at about 15 kilowatt or say 20 kilowatt, means 20 units per hour. 20 units per hour means you can say divided by about 15, 60 by 15 would be giving you 4 minutes. So 20 units, about 1.5 units. So that's about 10 to 14 rupees of electricity consumed. That's the cost of running this back to back on the job. If you look at the time saving, now this is where our focus will be more and more as you move along. Time today is going to be more valuable than money because you will have lesser time to produce more. Here you save straight away. Say you did 4 joints a shift, on average 25 minutes per joint in gas-based heating, and 4 joints you would have taken 100 minutes. 5 minutes for 1 joint in induction to do preheating. You could have done 20 minutes, you could have done 4 joints. 100 minutes for 4 joints with gas, 20 minutes for 4 joints in induction. 80 minutes per shift you can convert into productive time and get more jobs done. Same manpower, same equipment, more jobs done per shift. This is another classic case where we did preheating of pipes before submerged arc welding for the long seam. And then we did it post heating as well. This is a 12-meter long pipe, 25 mm thick. This is a 6-meter long pipe, about 65 millimeter thick. These two were, this is done. This is the equipment here you can see. And this is another one. Before induction, we had a huge gas bank here, which used to be maintained to continuously keep the pipe heated to about 400 degrees post welding and pre-welding to at about 200 degrees, 250 degrees. This is a classic case where we check that their welding time per length was about 20 to 25 minutes. So we calculated the power in a way that one pipe could be preheated while the other is being welded, so that your more expensive equipment, that is your column boom and the welding that is happening, doesn't stay idle. The minute you finished welding the first job, you put it onto the next station, you pick the preheated pipe from before and put it onto the welding station. Put a fresh pipe which is down, put the coil on top of that pipe and start your process again. In the next 25 minutes, this pipe will be ready to weld with the same temperatures of preheating that you wanted, with the same consistency. The time taken for the operator to pick and place this blanket, you can imagine, is nothing. He could just, two people could pick it, put it down, pick it and put it back up. The blankets are not getting hot. Mind you, the blankets don't get hot. This is a blanket stitched with Ceravol in between, so there is no heat on the surface of this blanket. We did calculations for them for preheating and post-heating, and we realized that for them, preheating a 40 kilowatt equipment was good enough to do it in 20 minutes. And for post-heating, they needed about 60 kilowatt equipment to heat in 20 minutes. So 40 kilowatt for preheating in 20 minutes and 60 kilowatt for doing it in 20 minutes. Another classic example is bearing to bearing housing fitting that you have to do. This is the last example I'll take. We are almost out of time as well, but bear with me for 5 more minutes and then we'll take your questions. So bearing housing to bearing shrink fitting is a classic example. Thicknesses are about 60 millimeters, diameters 8 inches to 64 inches. For shrink fitting, you need a temperature about 300 degrees. In shrink fitting, when you preheat the surface, it expands, and so you can put the cold part inside and fit it on top. And there should not be any drop of temperature during the fitting process. Otherwise, you will have a half stuck bearing or an incomplete weld. So this is the housing that was there, and the bearing had to be placed inside here. They are very close fit products. This is how we wound the induction coil on top of the bearing housing. I'll share a quick video with you to show you how easy the process was. It took merely about 6 minutes to reach the temperature. Look at the ease with which the operator is now fitting the bearing inside the housing. No rush. He's doing it at his own time because the bearing housing is always going to remain at that temperature, right? He is not being pushed. He's not being rushed into anything. Once he is done, they switched off the induction, simply remove the center clog, and their shrink fitting process is complete. Extremely safe. What is the alternative to this? Is dipping this bearing housing in an oil bath for 6 hours. It's in the oil bath for 6 hours. And if you had to do only one or you had to do 10 bearings, you would still have to fire up your oil bath, right? It would take 6 hours for the oil bath to reach its temperature. Here, you could do one job at a time. You could do one job in a day, do it for 6 minutes and put it aside. You don't need to fire up the oil bath for 6 hours to do anything. You could do it in 6 minutes, complete your job, dry, quick, easy, and clean method. No need to wait for the oil bath to warm up. Temperature maintained all along the process, so the operator is not rushed and he can do the job very comfortably, right? Again, to repeat the advantages of PWHT: quick heating, increased productivity, surrounding area doesn't get heated, coil is easy and safe to handle, no fire or flame due to induction heaters, it's a non-contact process, so you can be very safe and reliable heating process. Once trials have been finalized, the coil can be pre-made stitched into a blanket as you saw, so it ensures quick and easy setup.